This video is produced by the UCD Math Support Centre in conjunction with the UCD Access Centre. In this video we'll be looking at Argand diagrams and representing complex numbers in polar form. So complex numbers can be represented on the complex or Argand plane. The x-axis is the real part and the y-axis is the imaginary part of the complex number. So this looks very similar to the xy plane that people would know. Complex numbers with 0 as the imaginary part lie on the x-axis with all the other real numbers, and complex numbers with 0 as the real part lie on the y-axis. So complex numbers can be expressed in two forms. We have the rectangular form, which we've seen in previous videos, where z is equal to a plus ib, and we have the polar form, where z is equal to r times cosine of theta plus I sine of theta. In the polar form, r is the modulus of z, which is the square root of x squared plus y squared, where x is the real part of the imaginary number and y is the imaginary part of the number. Theta is known as the argument of z and is the angle between the number and the positive x-axis. So polar form is best understood by looking at an example. So let z1 equal to 1 plus I. In polar form, the modulus of this number is equal to the square root of 2. So we have the square root of 1 squared plus 1 squared. And theta for us here in this example, to find that, we take the tan of theta is equal to the opposite over the adjacent. The opposite for us is 1 and the adjacent for us is also 1. This means it's the opposite being the height of the complex number, so the distance from the x-axis to the complex number, and the adjacent is the distance from the y-axis or the origin to the complex number. And this gives us that theta is equal to the inverse tan function of 1, which is equal to pi over 4. And this in total gives us that z1 is equal to root 2 times cosine of pi over 4 plus I sine of pi over 4, or 45 degrees. Another example being z1 is equal to minus 1 minus I. Again, the modulus is the same. The distance from the origin to this number is still equal to root 2. And because we're talking about a distance, this number will be positive, always. The angle between the x-axis and the complex number is found in the same way, and we end up with cosine of 5 pi over 4 plus I sine of 5 pi over 4. Multiplication and division in complex numbers is much more manageable in polar form. So let's let z1 equal to r1 times cosine of theta 1 plus I sine of theta 1, and z2 equal to r2 times cosine of theta 2 plus I sine of theta 2. So this 2 subscript represents z2 and the 1 subscript for z1. So z1 times z2, as we can see here, we have our z1 number times our z2 number. And all we do here is we multiply the r1 times the r2 to give r1 r2, and what goes on inside is we get cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. This comes from the angle formulas and trigonometric formulas. For z1 over z2, we get r1 times cosine of theta 1 plus I sine of theta 1 all over r2 of times cosine of theta 2 plus I sine of theta 2. This is equal to r1 over r2 times cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. Again, we've used trigonometric formulas to arrive at this conclusion.